So these are the contents that I'll be covering. So basically, this paper proposes the use of data of sunrise, sunset times, along with the data of people's presence and shading around the street light in a predictive manner to achieve optimal operations of the street lights. So brightness required for by the street lights can be varied based on the number of people around the light, as well as based on the number of brightness around the light and the shading present. So by controlling the brightness, the amount of power consumed by the light can also be reduced, leading to reduced stress on the grids powering the street light. Problem statement is existing street lighting systems, they are time based systems. They lack dynamic context aware control, causing unnecessary energy consumption and operational inefficiencies in smart cities. The proposed method aims to design a machine learning based street light controller that adapts illumination based on real time environmental parameters, reducing energy usage while maintaining optimal lighting conditions. So objective was to develop a machine learning based street light controller that intelligently adjusts lighting based on real time environmental and contextual data, optimizing both brightness and operational duration. And to demonstrate that the proposed system effectively reduces energy consumption and maximizes power savings without compromising urban safety and functionality in smart city infrastructures. So literature survey, we have reviewed around 30 to 40 papers and came to the conclusion that by reviewing so many papers, we got to know that smart street lighting systems utilizing IoT, sensor technology, and adaptive controls have shown significant reductions in energy consumptions with the reported savings ranging from 38 to 95% while maintaining optimal illumination and safety levels. Integration of solar energy, motion sensing, and real time monitoring enables sustainable and cost effective street lighting solutions, reducing environmental impact and operational costs in smart cities. Advanced systems use machine learning, cloud technology, and computer vision for dynamic adjustment of lighting based on real time environmental traffic and activity data, supporting automation, predictive control, and enhanced surveillance. So the design, and this is the block diagram. Uh, Basically, the data, the sunrise, sunset data from different weather prediction applications have been taken, and shading around the street lights is ranked based on the environment around the area in the range of 0 to 1, 0 being for no shading and 1 for maximum shading. And number of people based on density of people around is also fixed to the range of 1 to 0, 1 being high number of people and 0 being low density. And so they are all given to the model, machine learning model, and to identify the number of lighting needed at any given point of time, then control the light status and brightness accordingly. And the main controller works by taking the sunset sunrise times for a day, the current time and the output of the prediction of the population shading around the street light to predict whether the street light should be on or off, and if on, what should be the brightness of the light. So the main controller can act as a central controller for multiple street lights together, minimizing the need of having a controller for every street light. Street lights only need to have a basic controller to take the commands from the main controller and in turn control the state and brightness of a street lights. So methodology, a system designed for controlling the lights needs to work continuously, generating the predictions and using that generate control signals for the light. The data collected for individual streetlights was stored in a database with each streetlight identifying by its unique identification number. This number was used as a reference to the system when the controller predicted the required state and brightness of the levels of the light. Decision tree classifier was used to predict the state of the light, whether it should be on or off. This brightness, for finding the brightness, it was not a classification problem as it wanted a particular brightness level to be calculated. So decision tree regression algorithm was implemented, and this regression algorithm was between 0 to 1, with the 0 indicating that light can be in minimal brightness, and 1 indicating that the light needs to be in the maximum brightness. And the operation, so this flowchart was used, and the operation of the whole cycle is repeated every 2 minutes to ensure that the state of the light can be controlled to the exact required levels continuously. So main controller accepted the input and sends the output predictions to the LED. Prediction is of light being on for the first check, because if the light is off, the brightness value becomes redundant. If the prediction labels that the light should be in the on state, the next prediction is what is the brightness. The required brightness of the light is sent to the controller installed with the light, which can generate the required pulse width modulated waveform to control the light. If the brightness prediction is say 1, then the light will be provided with full rated voltage to ensure complete brightness. If the prediction value is say zero point 0.5, then the mean of the required brightness, that is only 50% of the required value, and thus the amount of power will be only 50% of the rated power by the street light. Thus, by having the variation in the brightness to values less than the full value required by the environment around the light, the power consumption of the light is controlled. The light will also be provided with an option of manual override in case of user in case the user is around the light are in need of the power and more power than the predicted value. Manual override will be by default keep the light in full brightness for 5 minutes before it lets the controller have the control of the light based on the predictions. So implementation, the proposed system was simulated in MATLAB to test the accuracy of the predictions and to prove the system can be beneficial in real-time scenario. Machine learning models were trained using previously available data for the given location. To decide on the light on and off, the inputs required were amount of shading around the pole and the number of people around the pole. To be able to predict the number of people and the shading at the given location, regression-based decision tree models were trained. These models generated took the time of the delay, sunset and sunrise times as input and give us output the shading value and the population value. So to decide whether the light should be on or off, decision tree classifier model was trained, which had inputs as time and predicted values of shading and population. So this is the prediction model. Prediction figure 3 is the prediction model where sunset, sunrise, and time was taken as input, and they were given to regression tree as well as regression trees to generate to predict the shading prediction as well as the population prediction. And along with that, number of hours was given as the input for a classification model and regression tree. Classification for on and off, and regression for predicting the brightness of the light. Whereas in a time-based, that is classical control model, classical time-based model, what happens is the light will be turned on between specific times at night only and turns off early morning. So the time-based control has no option of brightness control and is always turned on at full brightness, allowing the light to consume the full power at all the times it is turned on. So these are the some of the results that we have got. Results indicate that the accuracy level is almost 80%. It is almost 68%. 70% we are getting. Almost 80% in which we are not. They are not that bad for parameters which have high variability in them. And in time-based control, we can see that the light was either on for about 30% of the time, and the same with the light being off. It is required for about 30% of the time, and for time-based systems, this accuracy can be improved just by changing the on-off times at the expense of power. So, to estimate the effect of correct brightness of the lamp, the predicted data was applied on a 150 watt LED light. So the data showed that for an average usage of light for 8 hours in a night, and the light was dimmed less than the full brightness for average of 3 hours at an average brightness of 60%. So we have calculated the total saving based on the brightness. This formula as power saving equal to full power minus brightness level into power into time. So the implemented system, the amount of power saved can be approximated to 180 watt hour for one street light in one day, which will amount to approximately 65 kilowatt hour over a year just for one street light. So these are some of the that's what I estimated. So the results that we have got. So machine learning based streetlight controller achieved nearly 80% of the prediction accuracy for variable parameters, outperforming traditional time based control methods. On off accuracy reached 100% with the proposed method, compared to about 67 for time based systems. Proposed model provided more suitable brightness level, dimming lights for 3 out of 8 nightly hours and achieving significant power savings. Estimated annual energy savings are approximately 65 kilowatt hour per street light using ML based approach. So the conclusion is the proposed method clearly indicated that the prediction of people and shading around the light can be used to control the lights effectively. Amount of savings obtained was also substantial per street light, and when the same is applied across the street lights in a locality or city, it can amount to considerable savings of power and reduction on demand from grid, thus benefiting the grid and the utility. Initial challenges in the system will be the availability of the required data for training of the predicted models for every light, but the collection is possible by placement of relevant sensors, and it will only need to be done once for the purpose of training. So that's it. Thank you. Is there are any questions you can ask?
So thank you, madam. So I have just one question. We have the registers like LDR. So can it be the proposed solution is much better than the use of LDRs?
Ha, sir.
So actually LDR we are using for again for the light control.
Yes, yes.
Can
Yeah,
you?
the LDR sensors can be used.
So my question is that whether the LDR is better option or the machine learning based model is better option.
Okay. Uh, machine learning
Oh, okay, thank you.
machine learning method is much better, I would say.
Okay, okay, madam. Thank you.
Yeah. Thank you, sir.
Hello? 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 Hello?
You are audible, ma'am. Your paper ID is 2303, na?
Yes, yes, ma'am. Can
Okay.
I
Start.
now start?
Yes, yes, ma'am.
Does my screen visible to you now?
Yes, ma'am.
Okay, good day everyone. My name is Raan and I'm the presenter of this paper. The title of our paper is Design and Development of Tire Thread with BLDC Motor Speed Control and Monitoring System for Unmanned Ground Vehicle in Mining Site Application. So this study was conducted in collaboration with my fellow researcher Dapo, Fanunya, Amarga, and Kandari, and yours truly. So the goal of our study is to design and develop a tire thread with BLDC motor speed control and monitoring system for unmanned ground vehicles or UGVs in mining application. Mining site present harsh and unpredictable conditions such as uneven terrain, debris which can lead to tire damage, and instability in UGV. Existing planetary rover wheels often lack necessary traction, which can lead to slippage and sinkage on challenging slope. The ability to monitor tire rotational speed is crucial for maintaining equipment stability and ensuring safe operation in these environments. Thus, our research addressed this need by exploring and developing a tire thread um, designed with rotational speed monitoring to enhance equipment stability and improve efficiency of mining operation. So our general objective is to design and develop a tire thread with BLDC motor speed control and monitoring system for unmanned ground vehicle in mining site application. So here we have a table um, yeah, that assembles based on their performance on different slopes. The study found that wheel assemblies designed for slopes greater than 10 degrees, such as tractors, quadruped research wheel assembly, have high traction. In contrast, those designed for slope less than 10 degrees, while rimless and mine gears UGV wheels have low traction. So the researcher's wheel stands out because it has high traction, low weight, making it suitable for UGVs that need to travel on rough terrain with low power consumption. It also only assembled that is uh, ROS ready. So the general framework of our study included the design and fabrication of tire thread the system architecture, block and schematic diagram, flowchart, and the gathering of statistical analysis. So in our paper, we use Bayes factor as a statistical tool to quantify the strength of evidence for one hypothesis over another. Essentially, it compares how likely our data is under hypothesis versus the other. This allows us to provide a clear measure of support for our findings. So based on this table, the strength of evidence against the null hypothesis was interpreted as follows. If the Bayes factor is 0 to 2, then there is not much evidence against the null hypothesis and it's not worth more than a bare mention. If the Bayes factor is 2 to 6, there is a positive evidence against the null hypothesis. Between 6 to 10, there is a strong evidence against the null hypothesis. If the Bayes factor is greater than 10, then there is a strong evidence against the null hypothesis. In other words, the larger the Bayes factor, the stronger the evidence against the null hypothesis and in favor of alternative hypothesis. So these categories provide a way to interpret the magnitude of Bayes factor and help the researchers evaluate the strength of evidence in support of the hypothesis. So for the specific objective, first, our specific objective is to design a lightweight tire thread with BLDC motors wheel assembly. So in this figure, we have two tire threads here were designed using SolidWorks 2022 and then printed using Crayly Indoor 3D printer. So these tire threads were attached in BLDC motor wheel assembly. To compare this weight of these wheel assemblies with a gear wheel, which is shown here in the figure, a standard weighing scale was used. So among the three options presented, we have here curve, chevron, and the gears. It is found out that chevron pattern is the lightest of 4.75 kilogram, followed by curve pattern of 4.85 kilogram, and the last option is 6.55 kilogram as shown in the figure. So for the second objective, we have to evaluate the wheel assembly's elapsed time on a lateral 15 degrees and 20 degrees loop inclination, slippage on a longitudinal 10 degrees and 20 degrees loop inclination. So for this inclination, we have this different testing of different inclination, slope inclination. So we have lateral and longitudinal slope inclination. Then it was found out for 15-degree lateral slope, both the chevron and chevron curve thread show strong performance. The chevron and curve both have 30 out of 30 success rate, while the gears thread had 20 out of 30 success rate. So here we have a figure the time it takes for each wheel to reach 1 meters. Figures A and B show that proposed thread design outperforms the gears. The chevron versus gears graph showed that chevron takes less than time to reach 1 meter compared to gears, while the curve versus gears graph also showed that curve take less time to reach 1 meter compared to gears. Since chevron and curve outperforms gears, they will compare to determine which was faster in reaching 1 meter at 15-degree inclination. Based on this figure, chevron was faster than curve, although in trial number 5, it was found out that curve was slightly faster. However, the difference between the speed was minimal based on this graph. So we also have here the comparison elapsed time to reach 2 meter on 15-degree lateral slope inclination. And here it is compared the chevron and curve to gears, with the former outperforming the latter. So the results show that gears had significantly longer elapsed time and considered a failure. Additionally, in figure C shows that chevron was generally faster than curve, except in trial number 5 also. However, in trials 1, 3, 5, curve was faster than chevron. Overall, on 15-degree inclination, chevron was the fastest, followed by curve, and lastly gears based on elapsed time to reach 1 meter and 2 meters respectively. So based on the Bayesian analysis, the study found that evidence that chevron thread's elapsed time was shorter than curve thread on 15-degree lateral slope, indicating it was faster in this test. So in the 20-degree lateral slope, the curve thread proved to be the most effective with a success rate of 21 out of 30. So based on the Bayesian analysis, the study found very strong evidence that the curved thread was faster than chevron on a 20-degree lateral slope. And for the 10-degree longitudinal slope, the curved thread also has the lowest average slippage at 17.97 centimeter. The chevron and gears threads had similar average at 26.2 centimeter and 27.5 centimeter respectively. The study also found that while gears thread was more stable, this chevron and curved threads had smaller slippage compared to it. So therefore, based on the Bayesian analysis, the study found positive evidence that the curved thread had less slippage than gears thread on 10-degree longitudinal slope inclination. So on a 20-degree longitudinal slope, the chevron thread had the worst performance, failing on all 30 trials. The curved thread had the best average slippage with 47.43 centimeters, followed by gears 51.83 centimeters. The chevron thread has the highest average slippage at 79.63 centimeters. So based on the Bayesian analysis, there's a positive evidence that the curved thread slippage is less than the gears thread of 20-degree longitudinal slope. With the third specific objective to design a ROS radio rotational speed monitoring system, so the system uses Raspberry 4 with ROS2 as its main communication hub. At Atmega 25060 microcontroller handles motor control, sending PWM signal to the CSC X11 BLDC motor driver to power the motor. For speed monitoring, a Hall effect sensor on the motor sends feedback at 250-60, which calculates the motor speed. The speed data is then displayed at 16 by 2 LCD and published to the Raspberry Pi via RUSTO for real-time monitoring. So here we have the schematic diagram for BLDC motor, and speed control shows the detailed view of its component under connection. The BLDC motor powers the wheel and is regulated by CSX11 motor driver and power supply with a buck converter. A built-in Hall effect sensor in the motor measures speed, and this data is transmitted to the microcontroller, which then sends control sense back to the motor driver. This setup ensures efficient and effective operation of the system. Also, we have here this paper, as I mentioned, uses ROS2 and BLDC motor, was validated against standard bicycle speedometer Coyote Velo 7. The result shows that the two systems had comparable performance, confirming the accuracy of the new system. The use of ROS2 also provides an advantage for more complex algorithm and remote monitoring in hazardous environments. So the system uses UART communication to connect at Mega 25060 microcontroller and the Raspberry Pi 4, allowing the system to publish real-time data ROS2 handle. This setup enables ROS2 devices to subscribe to the data for monitoring or controlling the motor speed, and it allows for implementation of more advanced control algorithm. So therefore, it has been the objective has been attained. So therefore, in conclusion, our study successfully developed a roster-ready system for rotational speed monitoring, and it was found out that chevron thread was identified as the lightest design. Most importantly, the curved thread consistently outperformed the other design on various slope inclination, demonstrating the best overall performance. The curve on chevron design also proved superior to the gears thread on the 15-degree lateral slope. For the recommendation, we recommend focusing on the design of the motor and motor driver to achieve the desired torque and power. We also suggest using more stable four-wheel chassis for testing, and if possible, conducting tests directly in mining environment for future validation. Thank you for listening. If you have questions, thank you.
Yeah. Thank you, madam. Very good presentations.
Thank you, sir.
Yeah, thank you. No questions from my side.
Thank you, ma'am.
Thank you, ma'am.
Next paper ID is 2306.
Yes, ma'am. Good afternoon.
Good afternoon, ma'am. Share your screen and start your presentation.
Okay, ma'am. Ma'am, my screen is visible.
Yes, ma'am.
Okay. Good afternoon, everyone. My name is Sakshi Thakur from Chandigarh University. I am presenting my paper on optimized hybrid learning for Alzheimer's detection and medication compliance. Firstly, we discuss introduction about Alzheimer's disease. Alzheimer's disease is a progressive neurological disorder affecting memory and cognition. Early detection can improve treatment outcomes and enhance patient quality of life. Traditional diagnosis methods are slow, costly, and often less accurate. AI and machine learning provide efficient and reliable Alzheimer's detection solutions. This study integrates optimization and hybrid learning for improved diagnosis accuracy. In next slide, we discuss about problem statement. Firstly, we discuss about problem what currently face the problem. Alzheimer detection is difficult due to overlapping symptoms and complex patient data. Like the Alzheimer disease is a neurological problem. Some symptoms are similar of Alzheimer disease. So in early, it is difficult to detect the problem. So, gap in existing studies focus on single modalities, limiting diagnosis, performance, and accuracy. Only in previous papers, I studies that they only discuss about only detection that Alzheimer is or not. I include with this. Also Alzheimer, firstly Alzheimer detection, and after that we include I add this framework in medication compliance. So and a limitation that in that this diseases current models lack guided optimization and hybrid DL integration. Like they only used ML models or deep learning. I integrated with model optimization and deep learning and machine learning integrated hybrid model, and need contracted Fox optimization plus bidirectional gated recurrent unit plus machine learning model random forest framework using multimodal data for accurate detection and compliance prediction. And next slide, we discuss about objectives. To develop an optimization guided hybrid model for early Alzheimer's detection and medication compliance prediction using multimodal data. To perform comparative analysis of the proposed model against state-of-the-art baselines, and to evaluate the models using metrics including accuracy, Evans score, AUC, and ROC for comprehensive analysis. And these are the papers literature review which I studied. And like early studies used SVM, RNN, and ensembles, but lacked multimodal robustness. They only use single data set only. And later research applied XGBoost with P8 and clinical data, improving prediction but needing external validation. Advanced GAN-based multimodal frameworks enhanced early stage detection, yet struggled with scalability and noisy imaging data. Deep models like ResNet 50, MobileNet, and DenseNet improved accuracy but faced dataset imbalance challenges. Few works integrated hybrid optimization with deep learning, leaving a gap this study addressed. They doesn't in previous papers they don't use optimization algorithm, but I integrate this. And this is the methodology. Firstly, dataset I use from Kaggle, Alzheimer's disease dataset, and and in next step, first I clean the dataset that by pre-processing techniques, label encoding, which category to convert into numerical values, outlier removal, reduce the noise, normalization, smooth balancing, and train test data split. After that, feature selection and fusion, random forest importance plus contracted Fox optimization, refine and fuse features. After that, we use deep feature learning, bidirectional gated recurrent unit, captures temporal patterns, dropout, and batch normalization, improve model stability. Hybrid classification, combined bidirectional gated recurrent unit plus integrated with random forest framework detects Alzheimer's and predicts compliance. After that, evaluation and compliance support, accuracy, precision recall, F1 score, AOC, ROC, and AI-driven reminder systems. Firstly, we detect the Alzheimer or Alzheimer. If Alzheimer detects, then we have to classify the compliance prediction. Like the patient is to be taken medicine timely or not, because Alzheimer disease is like a forgotten memory problem. That's the patient forgets to take the medicines on time, and that affects the treatment of that affects the treatment. Firstly, my model detects the Alzheimer, or if patient has Alzheimer, then we classify compliance or non-compliance prediction. And after that, compliant is to be that. patient do not take medicines on time properly, and non-compliant, which patient takes medication properly. So after that, we have to I created a model that we have to send the AI reminder system, triggered system. If the patient has forgotten is to be compliant, then we have to send the reminder of for taken to take the medicine properly. So this is the dataset description. Kaggle Alzheimer's disease dataset. Total samples 2,149 patient records with 34 clinical demographic, lifestyle, and cognitive features. Live cognitive features that can be included for symptoms to find Alzheimer's diseases, and train, and after that dataset splitting. Train test 80% of samples used for training. Test set 20% of samples reserved for testing. Classes two binary classification: Alzheimer and non-Alzheimer's. Features: cognitive features, behavioral data, demographic information, and clinical attributes. After that, balanced datasets mode apply to address class imbalance and improve model performance. And dataset preprocessing. Firstly, technique preprocessing is to be label including apply to convert category values into numerical representation. For example, if the dataset has attribute is to be like gender, male or female, that firstly text is converted into a numerical representation. Outline removal performed using IQL method for cleaner dataset. Like firstly, and after that, noise or duplicates that's to be removed from dataset. Only selected features useful data is to be added. Normalization ensures uniform feature scaling across clinical and behavioral data. Smooth balancing resolves class imbalance, enhancing minority class representation. Dataset split into training and testing sets for fair evaluation. Proposed model optimization. Firstly, I used optimization guided hybrid framework combining contracted fox optimization, bidirectional GRU, and random forest. Contracted fox optimization refines feature subset by simulating intelligent hunting behavior for accurate Alzheimer's prediction. Bidirectional gated recurrent unit captures temporal patterns bidirectionally, enhancing deep feature learning and improving model robustness. Firstly, in this proposed model, contracted fox optimization. Firstly, useful features has to be selected, and unusefulness features is to be reduced from dataset. And after that, bidirectional gated recurrent unit captures only deep temporal patterns, and bidirectionally, and also just some patient has to be visit doctor. So the doctor has to be checked both past data and present data, but other what faces the issue in past and currently stages, so that they can detect the problem. So, and random forest last classifies ensures reliable diagnosis and interpretable results for Alzheimer's and medication compliance. Integrated AI driven reminder system supports non compliant patients, improving adherence and clinical treatment outcomes. And these are the results. Proposed model performance. I used model that CFO plus BIGRU plus random forest. So this is the training and validation accuracy, and second is training and validation loss of proposed model and ROC curve, and confusion matrix, and proposed model compliance classification of Alzheimer disease, and model performance reminder system. And after that, I performance comparison also compared with I implement Napiers logistic regression decision tree model implement, and compared with my proposed model, and these are the best model because of the performance. And after that, I compared with previous papers with my proposed model, performance comparison of proposed model with existing approaches. And a conclusion. And Alzheimer's detection remains difficult due to progressive nature and overlapping patient features. Just like I earlier said, that this is the current issue because neurological problem has many similar symptoms. So we have issue to detect the problem in earlier stages. FCFO plus BIGRU plus RF, this model contracted Fox optimization integrated with bidirectional gated recurrent unit, integrated with random forest hybrid model, achieved 97.40% accuracy, surpassing traditional classifiers. Framework supports early detection and predicts medication compliance for Alzheimer's patients. AI-driven reminder system improves treatment adherence, ensuring continuity and better healthcare outcomes. And future scope is to test on the firstly. I will take the data set. I will in this I want to implement with the real clinical data set, and expand this paper its implementation for the use of mobile health apps for real-time monitoring and patient support, connect with smartphone devices to assist Alzheimer's patient daily, work with doctors to make the system more useful in healthcare. Thank you. Anyways,
Okay, so thank you, madam.
welcome, sir.
Yeah, thank you.
Thank you, madam. Next paper ID is 2309.
Hello, can you hear me, please?
Yes, ma'am. You are
Okay.
audible and screen is visible too.
Okay, good day everyone again. My name is Raan. Our paper is titled Design and Development of a ROS2 Ready Soil Sampler and Storage Payload for an Unmanned Ground Vehicle in Mining Application. So in behalf of my co-authors, Indron Amarga, Kandari, and yours truly. So in the context of modern mission of a human operator, an unmanned aerial vehicle and unmanned ground vehicle often work together. Unmanned ground vehicles are used to fulfill roles traditionally performed by humans such as transport, delivery, and scouting. However, manual soil sampling, a crucial task in mining, can pose significant risks to human workers, especially in hazardous or extremely hot environments. So our study focuses on addressing these challenges by developing an automated system. So our new sampler and storage payload system offer a major improvement over existing methods, unlike traditional sampling. So, which is inconsistent and other robotic systems like Agronaut, ClearPath Husky, and Falcon, which often fail to collect enough or pure samples. Our system excels. It's a more convenient and efficient solution that consistently collects multiple high purity samples of 20 milligram each, making it clear ideal for various field applications. So the main objective of our study is to design and develop a roster-ready soil sample and storage payload for unmanned ground vehicle, which is to be used in mining application. Categorically, we aim to demonstrate that the system can provide 12 isolated sectors, each capable of storing 20 milligram of soil experimentation, so that the drilling system can detect hard rock to prevent damage to the drill. So we have here the block diagram that illustrate the architecture and linkages of soil sampler and storage payload. The system receive command from ROS2 Ready Raspberry Pi, which communicates with Arduino microcontroller, controlling the high torque stepper motors for soil sampler collection. An IMU monitors vibration in the conveyor drill, providing feedback to the user via Raspberry Pi. A servo motor rotates the carousel storage payload based on readings from the IR sensor to align with the funnel. So the prototype design with SolidWorks is an 8 kilogram system built on lightweight aluminum frame. So it uses four NEMA 17 stepper motors to drive four conveyor drills, which transport soil to a storage payload. Additional motors control the Z-axis. IMU sensors on each conveyor monitor ground vibration to protect the drills. So the design uses readily available commercial parts and was fabricated using 3D printer at Caraga State University here in Butuan City. So we have here the flowchart that illustrate the logic of our system. First, after receiving a command from ROS2, the drilling system will lower the conveyor type auger drill to collect a sample. While drilling, an IMU sensor reads the vibration magnitude. If the vibration exceeds a predefined threshold, pitch greater than 15 and pitch less than negative 20, the drill will return to its initial position to prevent damage, and a feedback message will be sent to ROS2 microcontroller. Otherwise, the system continues drilling, collects the sample, and signals the soil sampling is complete. So here in our testing, we tested soil sampler under four different conditions: rocky versus pure soil, low versus high moisture. Our main objective was to test the sampler's ability to consistently collect a target amount of 20 milligrams of soil. So the null hypothesis here states the sampler will not collect this amount. The alternative hypothesis state it will. Repeated each test 20 times. To measure the sampler's performance, we calculate the probability of success by dividing the number of times it collected 20 milligram or more by the total number of attempts. A sample size of 20 trial is recommended for statistically significant result. The t-test is a statistical tool used to compare the means of two groups, helping researchers to determine if there is a significant difference between them. This is crucial for understanding the effectiveness of system in the treatment of specific population. So here we have the study found that the soil sampler consistently collected more soil than expected 20 milligrams in low moisture in 10%. A one sample t-test confirmed this finding statistically significant with p-value of less than 0.0001, which is far below the alpha level of 0.05. This indicates that the device is effective at collecting soil samples in this condition. The study found that also in high moisture pure sample, the soil sampler consistently collected more soil than expected. A t-test confirmed this was statistically significant, and the p-value was less than 0.0001, indicating strong evidence against the null hypothesis. However, the study noted that the clogging in this condition can be a problem and requires manual cleaning because of high moisture. And then, to ensure reliability and durability, the researcher conducted a test on challenging rocky soil, evaluating the soil sampler and storage payload's ability to withstand damage while collecting soil samples from dense and compact terrain. In rocky soil sample 90% moisture, the soil sampler collection was inefficient, often failing to collect samples. However, a t-test confirmed that the program threshold effectively prevented damage to drill, demonstrating its reliability in protecting the equipment in challenging terrain. This highlights that while the system is effective at preventing damage, its ability to collect sample is limited in this specific condition. Looking at here in table 6, you can see our system performance in pure soil. For 10% soil moisture, the system achieved 100% success rate collecting samples in 20 trials. In 90% soil moisture, while in strong, the success rate dropped slightly by 85%. Now moving here in table 7, which shows our system capability in rocky soil. At 10% soil moisture, the success rate is 80%, and for 90% soil moisture, the system achieved 85% success rate. This result demonstrates the system robust performance across different soil conditions, though with some expected variation in challenging environments. Therefore, in conclusion, this research enhances the effectiveness and capacity of rooster-ready soil sampling device and storage payload system for unmanned ground vehicle in mining application. It is capable of collecting 20 milligram of soil sample in multiple sampling sites with less amount of contamination, prevent the excessive damage to the soil sampler in challenging terrains and hard rocks. For future works and recommendation, we have here the recommended works that can be applied in future development of the system. First, use a gear shifting capability to utilize minimal amount of stepper motor and reduce the cost of the device. Second, the outlet of the conveyor drill will be bigger to avoid clogging of soil inside the conveyor. Thank you so much for listening, and God bless us all. If you have questions.
Yeah, thank you. So I had one question that what is significance of this particular problem? If you have provided the solution, so what is the significance?
Significance. Did I hear it right?
Yes.
So one significance of this is we have effectively show that we can successfully um, get samples using this at different soil moisture compared to other soil samplers. This would effective in effective in sampling compared to the traditional sampling, as different soil moisture was tested, prof professor. So it is capable of having in different soil sampling at different moisture, and also it has been collected in it has been tested actually in 20 milligram per tube as compared to the other soil samplers.
Okay. Now one more question that in your block diagram you have mentioned about the AI.
Again, Prof,
In your block diagram,
block diagram.
you have mentioned about the AI.
Yeah, so for the physical side of the uh, yeah, for the Raspberry Pi. Wait. For actually for the situation where let me check. So for the AI, actually more on the um, this the more on the what do you call this, the type of soil, sir, that is actually going through the Raspberry Pi at what yeah, sampling type of soil what we are trying to get. So that is the data coming from the AI environment. But actually, the scope of this study is more on the mechanism of the soil sampling of the soil, Prof. Not leaning towards the AI input, but more on the yeah, the mechanism on how it would get the samples.
Okay.
Mm-mm.
Thank you.
Thank you, Prof.
Yes. Patil madam.
Thank you, sir.
Okay. Thank you.
Yes, all questions are completed.
So
So we can leave now, sir.
okay. Thank you, madam. Thank you.